Hello and welcome to another video. Today we're going to be working on path with minimum effort. So in this problem, you're a hiker preparing for a hike. You're given an array of rows and columns, and so the height of a particular square is just the row and the column. And you want to get from the top left to the bottom right, and you want to get the maximum absolute or the minimum absolute difference between the heights of two consecutive cells. And what I mean by that is every time you move, there's going to be some height difference here. So like here there's 2, here there's 2, here there's 2. And for any route, you want to take the maximum possible difference, and that's the path with that's the effort of the hike. So essentially here there's a difference 2, 2, 2, 2. So the effort of the hike would be 2, but let's say you go this way, right? So here we would have 1, 0, 0, 3. So you take the maximum one out of all those. So the effort for this route would actually be 3. So you take all the efforts combined, and the biggest one is the effort, and you want to return the path with the minimal effort. It's a little bit confusing, but that's what it is. So in this case, like I said, we would go this way because the effort here is 2, where if you went something like this, it would actually be 3 because here's 3. Now we have another example over here. So let's figure out the effort here. So the effort here is 1, right? Because every single square, the effort's 1, 1, 1, and 1. Let's take a look at some other routes. So essentially you want to beat 1, and you can't beat 1 because the effort would have to be 0 for every single square, which obviously there's nothing there, right? So it would have to be like 1, 1, 1, 1, 1. So the effort here is 1. Now here, the effort is 0 because the whole path, the difference is 0. So essentially we need to figure out how we can do this. And it's kind of like a shortest path problem, except it's a little bit different because, you know, let's say this was like a problem where the number is maybe like how far you have to travel, right? So you start here, you travel 1, you travel 3, and so on, and you want to get like the shortest path. So we know how to do that problem, right? That problem is pretty straightforward, and the way to do that would be Dijkstra's algorithm. So let me write it a little bigger, extra large. So it would be Dijkstra's. And I don't really remember how to spell it, but something like that. And basically, it's a pretty straightforward algorithm. You simply make a heap, and you put all of your paths in there. So like here, you'd make a heap, you'd put your starting path in, you know, so let's say it's like row, column, and the distance. So it would be like 1, and then the row column would be something like this. You would put that in, and essentially what would happen is you'd have all of them in there, right? So you'd have some other distance, and you'd have some other like current cell you're on. And essentially you would always keep popping out the one with the smallest distance, and whichever one gave you the results first would be the answer, right? So you just put in like your current rows and columns, and you want to make sure that you don't go to the same one twice. And that's how you do a shortest path problem, right? You just literally keep track of what's the current distance of the path I'm in, and you're just greedily taking, okay, what's the shortest path so far? Let's traverse that path. And then once you get to the end, that would be your path. But here, we're not really keeping track of distance. We are more keeping track of this effort. So it's a very similar way of doing this. So what we're going to actually do is we are going to give the row and the column, but instead of giving the distance, we're going to give the effort. So let's just go through this example here. So essentially what's going to happen here is, let's actually move this down maybe a little bit more, just so we have a lot more space, right? So just move that down over here. We're going to go over this example here using the Dijkstra's algorithm. So essentially we're going to make a heap. We're going to put it over here just so we have more space, like I said. And we're actually just going to even get rid of this closing thing, right? Or we can make it like all the way over here just so we have a lot of space. So we're going to make a heap, and our heap is going to have the effort, which is 0 starting off, right? So we're going to start right over here, 0. And it's going to have the row and the column. So we could also label these as 0, 1, 2. Let's get rid of this. 0, 1, 2. So essentially we start at 0, 0 first, right? Because we want to have a heap, and we want it sorted by the effort. So the effort's going to be 0 at first. Okay. So now what we're going to do is we're literally going to pop, and then we're going to try to go in every single direction from where we're at, and we're also going to add this to a visited set, just to make sure we don't go to the same place twice. Because like if you visit this, you don't want to go to the same place twice, right? You don't want to keep revisiting the same route over and over and over and over. Otherwise, that would be like an infinite loop, right? So the way we're going to do that is we're going to have a set as well. And I'm just going to, in this example, every time I pop something, I'll just maybe like cross it out or something, right? Something along those lines would be fine too. Okay. So what we're going to do is we are actually going to, do that. So let's let's see what that looks like. So essentially, we're going to pop this 0, 0, 0. And we are going to go in every single direction from here. So we're going to pop, which means we're going to kind of like, this is visited. We'll circle it, meaning visited. We're going to pop this. So we're going to get rid of this, and we're going to put in new things. So from here, we have to go to every possible direction. So up is out of bounds, left is out of bounds, right is in bounds. So for right, we're going to need to put that in. So our effort was 0, but now what's our effort here? Well, it's 1. So we're going to put in 1, and we are going to put in the coordinates here. So this is row 0, column 1, right? And also, we can go down. That's valid as well, right? So we are going to put that in as well. So it's effort 2, and that's row 1, column 0. Okay, and now we're going to mark this as visited, and we'll just like cross it out or something to make sure we don't really care. Okay, so now we are going to pop out the smallest effort, right? We're doing Jigster, so we're just being greedy. So we're going to pop out this one, which corresponds over here. And this is going to... So we're going to pop this out, so we'll get rid of it. And now we have to travel in every single direction from here. So from here, we can go in 2 ways. So first we can go right, which is effort 0, but we originally had effort 1, right? So we need to say if we had effort 1, we need to keep track of the maximum current effort along the path, right? Because that's what we're going to be returning. So this is effort 0, but we're going to keep the max of the current one and the last one. So we're going to put in 1, and then we're simply going to put in the row in the column here. So this is going to be row 0, column 2. And we can also go down, which is effort 6. So we're going to put that in effort 6, and this is row 1, column 1. Okay, cool. So now these are the 2 that we visited. Or they're not really visited. We haven't really visited those yet, but now this is essentially what we have. And we visited this one over here. So now we're going to do the same thing. We're going to pop out this first value. So this first value corresponds to where, right? So it is effort 0 or effort 1, and then it's row 0, column 2, which is this value over here. So we're going to pop that out, and we're going to try to visit everywhere from here. So we're going to get rid of this, and we are going to try to visit. Well, it's actually, instead of just getting rid of it, let's just move it down here because we do need to check the effort. So the only place we can go is down, right? So if we go down, the effort is, like I said, it's 0, but we want to keep track of the biggest number we've seen so far, and we've seen 1. So we want to put in 1, and then this is row 1, column 2. So there we go. Now we can actually get rid of this because we've just used it. Now we can also, say we're completely done here. So now we do the next one, and we're going to pop this one out for the next one. So let's do that. So we'll just put it down here. So that's this value here. Now we can go left, right? So that's going to be effort 6. Going to be the same. And you can't mark something visited until you're actually there, because let's say the effort is less than. So the effort is also 6 here. So 6, 1, 1. And we can also go down, right? And the effort is 3 there. So let's do that. So we're going to add effort 3. And it's going to be 2, 2. Okay. And now we are going to actually get rid of this. We're completely done with it. And we can mark it like so. Okay, so now we're going to pop the smallest effort again, which is this one over here, right? 210, that's the smallest effort we have. So let's add that in. So I'm not showing this heap as sorted, but obviously it's going to be a min heap, so it will be sorted and it will give us the smallest value. So 210, what value is that? That's actually this one over here. So from here, we can go this way. So let's add that in. So that's effort 5, and it is 1, 1. Okay. Now we can also go down, and that is effort 2. So we'll add that in. So it's effort 2, and it is row 2, column 0. There we go. Now we've fully used it, so we can get rid of it. And by get rid of it, I just mean like we're going to add it to the visited set. So we're completely done here. Now we're going to pop the smallest again, which is this one here, smallest effort, which represents where again? So that's going to represent effort 2 at 2, 0, which is right over here. And we can go here from here. So this is going to be effort 2 again. And it's going to be 2, 1. Now we're completely done with it. And then we can mark this as visited. Now from here, we're going to pop this one again, because that's the smallest effort again. And now where can we go from here? This is this value here, so we can go up. We still haven't visited that yet. So that's going to be effort 5, and it's going to be 1, 1. And we can also go right, which is effort 2, and that is our greatest value so far. So 2 and then 2, 2, right? So now finally for our last step, we are going to pull this value here, because this is our smallest effort again. So we are going to pull this value here, and we're going to say, oh, look, this is our actual, this is the end. So then we can just return the effort here. So you see how, like, even though we took this path first, because this was so expensive, we kept pulling out the cheapest effort first. So we actually got this path first, right? And that effort was 2. So that's pretty much it. So you make a heap, you keep track of your maximum effort seen so far, and as soon as you get to the end, you're guaranteed to get the minimum effort to get to the end. And that's pretty much the algorithm. So it's Dijkstra's algorithm with a heap, pretty straightforward. You just, instead of keeping track of, the current distance, you just keep track of the maximum effort seen so far every time you go down the path, and then every time you add a new node, you just say, okay, for this current node with this current effort, what's the maximum effort here? Is it this new one that I've seen, or is it the old one? And you keep track of that, and you're guaranteed to have the minimal effort once you get to the end that if you use a heap. So let's actually code that up now. And let's actually, I believe we can full screen this. So there we go. You can see it a little bit better. So we are going to make an m by n. So we can say mn equals length heights. And then length heights 0. Now we are also going to make a directions, right? So let's do that. As always, because we can go in every single direction. So 1, 0. And you can make this tuples or array. I'll make it tuples this time, but you can make it an array of arrays if you want as well. So 0, 1, and 0, -1. And there we go. Now we're going to have a visited set. So visited. And finally, we're going to have a heap with some default value, right? And the default value will be the actual value of the, like, what do we want to call that? We want to call that the effort, right? So it's going to be 0 and then index 0 here. Okay, so we can say while heap, we're guaranteed to find a result. We can say effort, and then the x and y coordinates, effort x, y equals heap, and we can say if x, y equals the end values, right, which is m minus 1, n minus 1, that means we actually got to the last node. We can just return the effort because we got to the last node, which is where we want to be. Otherwise, we can check if x, y in visited. Then we've already seen it, so we don't have to do anything. We can just continue here. Otherwise, we need to add to visited. So we'll add x, y here. And so I guess that's why you also want to have, actually that part wouldn't matter. No, this is fine. Okay, so we need to add x, y, and then we need to actually get new directions, right? So we can say for something new, so we can call it like dx, dy, or we can call it like nrow or whatever you want to call it, right? I guess maybe we can also rename these. If you wanted to, you could. So you could say like for row call, and then this could be row. So it's like a better variable name, right? Instead of x, y. Seems a little bit better. So there we go. Row call. Now we can say for something, so we can say like RC or something maybe in directions. New row equals row plus R, and new column equals col plus C, something like that. Now we need to check if these new rows and new columns are actually in bounds, right? So we're going to say if 0 is less than or equal to new row is less than m. So maybe this is also should be renamed. So this should be like rows and calls or something, right? That's probably better. So we can do that as well. So this is rows, calls, just better variable name. Why not, right? So if new row is less than rows and 0 is less than or equal to new call is less than columns, and we could say new row, new call, not in visited, right? We don't want to add things that we've already visited, no point there. We could say new effort equals maximum of the old effort, or the absolute value of, and then this is going to be heights, new row, new column, minus heights of the old row and row column, right? So row column. So we're going to get the difference there, get the absolute value, see if it's bigger than the effort, and store the biggest effort there. Now we have to heap push. And we need to do, we're pushing to the heap. And what are we pushing? So we're pushing new effort. And we are pushing as well new row and new call. Also, like I said, you can push a tuple, you can push an array, it doesn't really matter. And you are guaranteed, I believe you're guaranteed to get a result here. I don't think you'll ever get anything that wouldn't work, but just in case, let's return -1 here. But we shouldn't really get anything that never works. So let's see what we have. Let's actually stop the minimize so we can actually see if we got an answer. It looks like it's accepted. Let's submit. Okay, so it looks like it's accepted, and as you can see, it's reasonably efficient. So let's go through the time and space complexity for it. Let's full screen again. So let's go through that. So for the time, what are we doing, right? You always want to think about it. So we make rows, we make columns, that's nothing, that's nothing, that's nothing, that's nothing. Okay, while heap. So how many elements can we have in the heap maximum? Well, we're always checking if it's not visited. So we can add something, multiple times, but it's not that many times. So realistically, we're going to add something roughly m by n times, right? If m and n are the rows and the columns. Like we can add something multiple times technically, but it could be a little bit over, but it can't be like, you know, an order of magnitude over. So it's going to be m by n that you like, that's going to be as many items as you can have, right? But also for every single one of these elements, we do a heap push and a heap pop. So that's also going to be log m by n, because if the heap is m by n, every time you do a heap push, it's log of the size of the heap. So it's m by n times log m by n for the time. And for the space, also pretty straightforward, right? Our heap and our visited set are going to have roughly m by n items in it. So yeah, that's actually going to be it for this problem. Hopefully you liked it. Not too bad. Normal Dijkstra's problem, you just have to change, you know, calculating the distance. Instead of that, you have to calculate the maximum effort seen so far, but it's basically the same thing. So hopefully you liked this problem, and if you did, please like the video and subscribe to the channel. And I'll see you in the next one. Thanks for watching.